about the lead controllers. And jack contributed controller and lag controllers. And also we might have the lead lag, and this one depends on the time. And so we have different types, and most of the industry they're using is a PID controller, so that means combining proportional integrators and a derivative one. Okay. So I will going to go over this one piece by piece. The first one is so this is our systems. S+1, S+2, and S+10. Okay, and here we place our controllers here. So here is K. So this is our P control. P, that means proportional control. Okay, or sometimes people refer to the position control. And then we take the unit feedback here. And you might ask me why you consider the unitary feedback, because that is the simplest one. And as long as we learn the principle, you can always apply the principle to various kinds of the feedback configurations. Okay, so we'll take this one. So now for this case, we want to determine maybe for the first one, we characteristic equations is 1 plus k and 1 S+1, S+2, S+10 equal to 0. Okay, so to obtain the characteristic equations, you need to find what is C over R. Okay, so for example, let me call this is a GS. So C over R is Kg and 1 plus Kg. So from here, we know the characteristic equation is the denominator of the closed loop functions. So 1 plus Kg equal to 0. That's what we need here. Okay. And so from here, we can maybe using the MATLAB to help us quickly plot the loop locus and get the readings here. So let me close the two windows. And again, in this figure, the program, I put a figure here. If you don't like to generate too many figures, remember you delete it and before you save it. Otherwise, every time you run the program, one new figure going to generate it. Okay. So sometimes myself, I don't like that one. So anyhow. So now we're going to plot, and here let me start from here. If you want to clean the window, CLC. Yeah, CLC basically clean up the window for. And for this case here, our numerator is equal to 1. Denominator is equal to, I don't know, 1 plus 3 plus 2 and 1 plus 10. 20, 30, 10, and 2, 3, 1, 1, 13, 32, 20. Okay. Okay, so that is a system. And for these systems, and you can see basically the system has the certain conditions. So for example, here the K value shouldn't be larger than this. So I roughly click it, and so for example, roughly 400 some. So if K value is larger than certain critical value, then the system will become stable. For example, here the root here corresponding K value equal to that much, then we have a positive root. So that one we want to avoid it. Okay. So under these situations, and basically this region, you can see the roots in this region we call the dominant roots. dominant pole, dominant roots. That means the location of the roots there basically dominant the behavior. The third one will be here. Okay, here with 3 branches, the third one is here. Again, this one corresponding, that one, the third one basically in this region, that corresponding to the time domain will decay very, very fast. So here I would say our concern is not here, our concern is here. So in this way, I want to rooming. So the rooming basically, there's no way for MATLAB to draw it. So I'm going to change the scales. So I'll go for, okay, this one. So I want to look for maybe from 10 to 10. Okay, how about this one? So, okay, so that is rooming. And again, remind ourselves, we have a third root here. Okay, the third root here, that is our last concern. So we're looking for here. So let me delete this one. Okay, so right now from here, basically you can determine, so given this system, you can determine K. Again, depends on how much you want the zeta. For example, zeta 45 degrees. Zeta 45 degrees corresponding is 0.70, I'm sorry. 5, okay. So basically here you can know the damping ratio, you can know the frequency. Here the frequency is omega n, okay. And also you can determine K. So from here you can move the cursor in MATLAB and you can quickly determine the value. Or otherwise you can also calculate precise value. And so for example, say I ask you, say the question could be say if say s equal to -1 plus j1 on the root locus. So that back to our questions we exercised in homework 6. Whether this point is on the root locus or not, then maybe you can try to visualize the answer is no. Okay, or otherwise you can utilize the phase angle criteria and justify for this one. Okay. The second question is this: if say I wish the damping ratio equal to 0.707, and also I wish omega n is greater than or equal to something, zeta omega n. Basically, follow up our previous questions is less than greater than say 4. Okay. So once we have this one, then we can determine the locations there, similar back to our previous examples. So for this question up to here, I would say that given our status now, I think the determining the value of K should be very straightforward. Any questions? Okay. So we can pick one. So for example, here we want to pick, say, K equal to this one. Okay. So for example, I want to determine K equal to 165. So if K value is 165, and you want to see how the performance would be. So now we can do the little bit calculations. So for example, say determine the value of K equal to 165. Now the follow-up is we want to check the performance, the result. So here we back to here. We simply plug in K equal to 165, then we can use the old approach. For example, say we can check the unit step response, the unit impulse response, unit ramp response, etc., to really look into what the system looks, the dynamics looks like. Okay, so basically that is, you can refer to this as the post-processing analysis. So say we want to determine the unit step response. Okay, for the unit step response, our characteristic equation is again that one equal to this one, kg 1 plus kg, and for this one, we can rewrite, so G equal to this, and that one we can rewrite into a little bit troubles here. So K, S plus 1, S plus 2, S plus 10, plus, if I make a mistake, help me, plus 10. Okay, so that is a closed loop transfer functions. Now we're given unit step input, so that means R equal to 1 over S, right? So given this one, then the C, you can calculate CS and equal to plugging, and then you can take the Laplace transform, you can take the CT. So for this one, suppose you can do the analytical calculations just like our module one, back to about a long time ago, right? So we have such techniques in place, assuming you know, but most of the time I believe you have to turn over your notebook for the detail, but assuming everyone knows, so we should be able to, we are capable of doing this. On the other side, we can use MATLAB as well. So for example, if we use MATLAB, so for that case, okay, so now our job is to determine plot the unit step response. Okay, so that one, based upon in this way, we're going to use is the unit step is response is going to use the MATLAB command step. Okay, and use that command step, and basically that step is the numerators of the closed loop function, denominators of the closed loop functions. Okay, so this one numerator denominator is different from here. Okay? Good. So numerator, let me emphasize C. C means closed loop. So that one will be K, right? So let me give the K value. So K equal to 165. That is what we determined. So numerators of the closed loop is K. Denominators of the closed loop equal to, again, you can implement the numerator there, the denominator there. That should be 1, 13, 32, 20 plus K. Okay, and system of the closed loop equal to transfer functions. Okay, so now we're going to plot, and that is that, whatever, okay. So hopefully this is right. So that is a 1 here. So from here you can have a feeling about the dynamics, and this dynamics basically, here you can see they basically nearly from here we can see they get into the steady state is pretty much take 9 or whatever the 9 seconds. And if you are more interested in determining whether this is will go to the steady state is 0 or not, then steady state error you can analyze is this. So for example, the ESS equal to limit s approaching to 0 and E times S, right? So what is ES? Looking at here, this is our E. Okay, so in our calculations, and basically you can see the ES equal to R times C. So basically that is R times 1 minus C over R. So C over R we've been calculated here already. So E should be equal to R times 1 over and to that one times this one, 1 minus that one, so that should be something like this. Okay, hopefully my calculation is right. So basically, again, one mistake, multiply with S, Okay. So now plug into here, so therefore the ESS will be equal to, plug in those things will be 20 plus K. Okay, so for this case, the nervous system will go to the zero steady state error. However, the larger the value of the K you choose, then that will make the steady state error smaller. So that is the one we obtain. So now the question is this. So basically right now we have our controller designs and from here, and we plot it. And from here you can see the overshoot is pretty big, about 40%, 39 or 38%. And also steady state error is never been zero. Given this design, I would say this design working, but not good. Okay. And for example, if you want to say reduce the peak, then say to less than 20%, then basically you need to go back to here to modify the zeta. If you remember, zeta is a parameter governing the peak. The larger the zeta, the system has more damping, then the system will have less oscillations. Okay. So if you don't like the peak here, you better to have a larger zeta here. So that's a way for you to choose from. And if you like the system have a quicker, so for example, you see that the cycling time is about 9 seconds, 8 seconds. If you want that one to be shortened, then you basically you have to work on this one. Change these numbers here. You good? Okay, so that is the situation for this. And by all means, doesn't matter how hard you try to change the K, this system won't be never able to get into the zero steady state error. So if you want to say another additional design criteria is I want a final system to have a zero steady state error, then likely you're going to change this type. P type, the P control won't be sufficient. Then you have to consider other type, for example, integrated I control or PI control or whatever. Okay? So that's kind of the thinking process. And in our controller design, we always starting from the simplest one. If the simplest one working, then we don't need to go for the expensive one, because more complicated, that means more expensive. Usually for the controller design, that governing, that kind of related is the electric circuit. If you remember the op-amp, we have in our modeling, we described a little bit, right? For the op-amp, we have the minus, we have positive, and say here is non-inverting. So basically here we have some kind of the complicated circuit here, and going to play the role for say constant or PI or PD. Okay, so the more things you want to try and then more complicated in this circuit here, they're going to spend for that one. And sometimes if one stage of the op-amp won't be enough, you have to stack the two things together and for the purpose. Okay, so that is for this one. Then continue. My goal is hopefully we can finish all the controller designs in 2 weeks by end of next week.